Okay, this is lesson 2.3, solving polynomial equations. Let's talk about real roots. Real roots are the x-intercepts of the polynomial graph. So graph crosses the x-axis. We call these roots or zeros or x-intercepts. So the real roots of a polynomial equation correspond to the x-intercepts of the graph. Extraneous roots can happen as well. So a solution to an equation that seems to be right, but when you check it by substituting whatever you solve for x into the original equation, turns out not to be correct. And we'll see some examples of where that can occur. So the whole point of this lesson is just to go through some lesson examples on solving for the roots. So essentially, you have an equation for representing your polynomial. You want to know where is that polynomial equal to 0, right? Where is p of x equal to 0? So setting your equation equal to 0 is always going to be our first step. So here we have an equation: x cubed minus x squared minus 6x equal to 0. And so the way we do this is we factor and solve, just like many equations we've done in the past. Factor and solve. Okay. So we start off an equation where every term has an x. So we can start by doing greatest common factoring. Okay, greatest common factor. We don't need to jump right into synthetic division just yet. Okay. So x can be factored out, and that leaves us with x squared minus x minus 6. And don't forget to write equal to 0. Okay. So with the x factored out, we have a quadratic remaining inside our bracket here, x squared minus x minus 6. And we can do some simple trinomial factoring here and recognize that I could further factor this quadratic as x minus 3 and x plus 2, right? Two numbers that multiplied to -6 are -3 and 2, and -3 and 2 add up to -1, which is that coefficient in the middle term. Okay, and that's equal to 0. So from the fully factored form that we see here, we can obtain three solutions. One is x equals 0, so that factor can be 0, so the whole thing is 0. Multiplied by x minus 3. X minus 3 says, well, if x is 3, then that factor is 0. Okay. And if you wanted a 0 from x plus 2, then x would have to be -2 for that factor to be 0. So therefore, we have x equals -2, 0, and 3. Okay, so if we're okay with that first example, let's look at another example. Example B. 2x cubed minus x squared minus 18x equals -9. So oftentimes when we see another number on the other side of the equal sign, we will move it over, or essentially add negative, or add 9 to both sides, so that we can get one side of our equation equal to 0. Okay, so let's do that first. We're going to have 2x cubed minus x squared minus 18x plus 9. So we're going to add 9 to both sides, and then the right side becomes 0. -9 plus 9 is 0. So now we're going to have to use factor theorem here to factor this polynomial. So we're going to look at some possible factors first of 9, right? So we can have an idea of what my divisor will be. So I could say, what are the factors of 9? The last term here, the last constant term. We can have plus or minus 1. We can have plus or minus 3 or plus or minus 9. These are all factors of 9. So by factor theorem, I'm going to start checking. Right, and I'll just go in order from the smallest number to the largest. So if I start with f1, so f of 1 equals, plugging it in, 2 times 1 cubed minus 1 squared minus 18 times 1 plus 9. Well, that does not equal to 0. Okay, so we don't have a 0 there. If I tried -1, f of -1, we will get 2 times -1 cubed minus -1 squared minus 18 times -1 plus 9. That does not turn out to be a 0, so that's not 0. That will not work as a factor. But let's move on to the next one, f of 3. So if I try that, 2 times 3 cubed minus 3 squared minus 18 times 3 plus 9, well, that turns out to be equal to 0. Okay. So with x equal with 3 as a factor, it satisfies factor theorem, then we can say, therefore, that x minus 3 is a factor. And then identifying a factor, we can use that factor now to carry out some polynomial division to determine the remaining factors for this polynomial. So let's apply synthetic division. So with synthetic division, I'm going to start by drawing my chart, put out the coefficients of the polynomial. So 2x cubed would be 2, minus x squared, so we have a minus 1, minus 18x, so that'll be minus 18, and then the plus 9 at the end. And then my kind of divisor, so to speak, here would be on the left side, 3. And we carry out the steps. So we bring down the 2, multiply by the 3, we get 6. Add -1 and 6 to get 5. 3 times 5 is 15. Minus 18 plus 15 is minus 3. And then 3 times minus 3 is -9. 9 plus -9 is 0, which is what we expected if this was a factor. X minus 3 was a factor. Okay, so we have now 2, 5, and -3 as the coefficients for the quotient, which is going to be a quadratic. Right? So my equation now becomes 0 equals x minus 3 times 2x squared plus 5x minus 3. And all I did was I put a 0 on the left side now, but the whole polynomial on the right side is now the factored form. It's not fully factored just yet. I have a quadratic that can be further factored. So 2x squared plus 5x minus 3, complex trinomial. And we can factor that. We're going to get a 2x in one of the brackets multiplied by an x to get that 2x squared. And the remaining numbers here are going to be -1 and 3, right? So -1 plus 3 gets me that -3 at the end, and then minus x plus 6, 3 times 2, 6x, it gets me plus 5x there in the middle. So that works. Okay, so there's our fully factored form. And from this fully factored form, set that equal to 0, we can get 3 solutions, one of them x being 3, the next one being -3, and for the middle factor there, 2x minus 1, that solution will be 1/2. So there are our 3 solutions to this, or 3 roots or 3 zeros for this polynomial equation. Let's look at another example up here at C. So here's one that involves a little bit of work to set up. Okay, so for this kind of question, we can't just, well, we could add 8 to both sides, but we still have this x factored out of the rest of the polynomial. So let's expand that first, right? So let's expand that so we get to 3x cubed, right? And then minus 2x squared, and then the minus 12x. And then if we add 8 to both sides, we can get plus 8 here. And on the right side, we get 0. So I expand first so I can get a fully standard form looking polynomial. And then we can proceed to fully factor it, right? So that we can now include the 8, fully factoring this. So let's look at some possible factors, right? So possible factors that satisfy the factor theorem will come from that last term, 8. So some possible factors are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. These are all factors of 8 that we can try. Okay, so if you work it out, let's try f of 1. So that's going to be 3 times 1 minus 2 times 1 minus 12 times 1 plus 8. That does not look like it's going to be 0. Okay, let's try -1. 3 times -1 cubed minus 2 times -1 squared minus 12 times -1 plus 8. And that does not look like it's going to be 0 either. But if we tried f of 2, I forgot some cubes and squares up here. Okay, if I tried f of 2, let's see what that one looks like. 3 times 2 cubed, that's 8. So 8 times 3 is 24. Minus 2 times 2 squared, that's 4 times 2 is 8. So 624 minus 8 is 16. Minus 12 times 2 is minus 24. So that brings me to minus 8. And you add 8, that brings me to 0. So there's our factor there. So therefore, x minus 2 is a factor. And recognizing that we have one factor already, we can carry out synthetic division to find the rest. So let's carry it out. Let's write the coefficients of my polynomial: 3x cubed minus 2x squared minus 12x, and then we have the plus 8. And we're going to be dividing that by the factor there, 2. So let's do that. So 3 comes down, right down to 3 in the third row, multiply it by 2 to get 6. Put that in the second row in the next column. Negative 2 plus 6 is positive 4. Write that in the third row. 4 times 2 is 8. Write that in the second row on the next column. And negative 12 plus 8 is negative 4. Write that in the third row. 2 times negative 4 is negative 8. And we write that in the second row on the last column. And then 8 plus negative 8 is 0, as we expect, since x minus 2 is a factor. So 3, 4, and negative 4 are the coefficients of the quotient, which is going to be a quadratic quotient. So my equation now becomes 0 equals the factor we already obtained, x minus 2. And then now the quotient here, 3x squared plus 4x minus 4. Okay, it's not a fully factored thing yet. If we can further factor that quadratic, right? So if we can, then we do so. So x minus 2, 3x squared. Let's see, we're going to have a 3x, and we're going to have an x, right? Okay. And how do we get a minus 4 at the end? Well, we're going to have a 2 times 2, minus 2, minus 2. No, one of them will have to be plus, right? So 2 times 3 is 6x, minus 2x is positive 4x in the middle. So that works. Okay, so then we have now 3 solutions. Therefore, x equals 2 from the first factor. We can have 2/3 from the second factor and minus 2 from the third factor. So those are our 3 solutions there. Okay, so those are just some kind of different kinds of ways to solve an equation that's given to you in various forms. Let's look at the next page, example number 2. Determine the real roots and the extraneous roots. So let's talk about extraneous roots. Well, we can have, let's start solving for each of these roots. This is already in factored form, right? So if I took the first factor, x cubed plus 1, and I set that equal to 0, what value of x would make that factor equal to 0? Well, if I do that, if I solve for x cubed equals minus 1, if I subtract 1 from both sides, and if I take the cube root, like x times x equals negative 1, if I took the cube root of both sides, I will have x equals the cube root of negative 1, which is just negative 1. If you're confused with what I'm doing here, cube root, another way of looking at it would be to take x to the third, raise that to the power of 1/3 on both sides, right? That. So just performing the same operation on both sides and balancing the equation. So x to the power of 3 to the power of 1/3 just cancels itself out. X equals negative 1 to the power of 1/3, or you could say this is the cube root of negative 1, which is just negative 1. Okay, so that is one solution. Let's look at the second factor, 3x squared minus 2 equal to 0, right? So what value of x makes that factor 0? Okay, so if 27, 3x squared minus 27 equal to 0. So if I add 27 to both sides, 3x squared equals 27 on the right now. And then if I divide both sides by 3, I'll get x squared equals 27 over 3, which is 9. And if I take the square root of both sides, x is the square root of 9, which is plus or minus 3. So now I have 2 more solutions there, plus or minus 3. And if I look at the third factor, x squared plus 4, what values of x will make that 0? So I'll have x squared, if I add and subtract 4 from both sides, I'll have x squared equals minus 4. Okay, and so x, if I took the square root of both sides, I'll have the square root of minus 4. Well, that's kind of invalid. Let's just say x is invalid. Okay, x, so that would, there is no real solution, right? No real solution. There is something called the imaginary plane of numbers. There would be an imaginary solution because we define an imaginary number I equals the square root of negative 1, but that's not part of our course. We only deal with the real numbers in our course. So we'll treat this as no real solution. Oh, solution, what am I solutionary? Okay. So we're going to say x is invalid, and so we call x squared plus 4 an extraneous root. Okay, it's an extraneous root, not a real root, it's an extraneous root. All right. Can we find some other roots? Let's look at another example. F of x equals x to the power 4 minus 25x squared plus 144. Okay. So in a question like this, before you, okay, you're going to think about this and go, okay, I'm going to factor this. I have to factor this, get the factored form. Okay, x to the power 4. That might mean I have to do a couple of synthetic divisions, a couple of like multi-layered steps of synthetic division to get to the final answer. 144 is a big number. 144 has many roots. Sorry, possible factors, I should say. Possible factors. Am I going to be really testing them all? So it could be a very long and involved problem, unless you're clever enough to think of a little bit of a shortcut. And if you look carefully, this term here, x to the power 4, and then minus 25x squared, we skip the cubic, right? So these are kind of even degree terms. And if I divide by 4, I get 2. Like this is like 1 dimension less than the previous term, kind of, so to speak. It looks very similar to what could be a quadratic if you do one little tiny change, right? And this is something I'm going to introduce to you, and it's kind of common in a lot of other courses, calculus and those kinds of and algebra and stuff like that. It's something that we call substitution, a special kind of substitution. If I took like a dummy variable, let's use the letter u, okay? And what if I said u was equal to x squared? Okay. So if u is equal to x squared, then I could say u times u would be x squared times x squared, which is just x to the power 4, okay? All right, so why am I doing that? Because if you took f of x, this whole right side here, and you made an adjustment here, if I said, well, instead of x to the power 4, what if I just said u squared, right? Minus 25, and instead of x squared, I change that to u, and then I have plus 144. So essentially, I'm replacing anything that's x squared with a dummy variable called u. And by doing so, I get this kind of formula, this polynomial that looks like a quadratic. Okay, it looks like a quadratic, something that we can solve. Okay, so this is now a function of u, right? So f of u. All right, and so we can only do this because there was no x cubed term in there, and there was no x term in there, right? So if I do this, I have something that looks like a quadratic, and this is something that I can factor without using any polynomial division whatsoever. And when I factor this, yeah, you write down your factors, and you think about, okay, what two numbers multiply to get you 144 and add up to negative 25? And you'd be right if you guessed 16 and 9, right? 16 times 9 is 144, and 16 plus 9 is 25. But these have to be both minus. So u minus 16, u minus 9. And there's our factored form. But that's with the dummy variable u. I can simply take the variable u and turn it back into x squared, right? So I can say u is x squared. So make that change, u becomes x squared again, so x squared minus 16. And then u is x squared again, so x squared minus 9 for the second factor. And I'm left with a pair of quadratic factors here, which you might recognize to be each of them a difference of squares, right? This is x squared minus 4 squared. And this one here is x squared minus 3 squared. And so I can, using my knowledge of difference of squares factoring, I can obtain the result x plus 4 times x minus 4 from the first difference of squares. And then for the second one, x squared minus 3 squared, I can get x plus 3 and x minus 3. And now I have the fully factored form of our original f of x. Okay, and so that is kind of a shortcut way of doing this. Otherwise, you'd end up doing maybe a whole page and a half of synthetic divisions and factoring. So here are my solutions. X equals -4, +4, -3, and +3. Okay, so here's one for you to try. And for this one, you're going to have to carry out the synthetic divisions here. So why don't you pause the video, and then when you come back, you'll get the answer to check. Okay, so hopefully you've had a chance to carry it out, and you discovered that x -3 is a factor. So when you carry out the synthetic division, you can get the remaining quadratic factor. And so your fully factored form is x -3 times x squared plus 1. But upon trying to solve for the roots, you'd get, well, you set this equation to 0. I forgot to write that here, x -3 times x squared. X -3 times x squared plus 1 equal to 0. And so you get x equals 3 is one solution. But for the other factor that you have, x squared plus 1, if you tried to solve for x, you'd end up in that situation where you have the extraneous root. So that's the answer for that one. Okay. And let's see what we've got next. So let's just try an application problem. The length of a square-based jewelry is 5 centimeters more than its height. The box has a capacity of 500 centimeters cubed. Determine the dimensions of the box. Let's say this is a box, square-based jewelry box. I probably forgot to put that word in there. Okay, so let's see the square base. Let's try and draw a picture of this square base, and something like that. Very rough sketch. Okay, so if x is the height, then the base is 5 more than the height, so x plus 5. And because it's a square base, the length and width are both the same, x plus 5. Okay, so I'm saying my square base is, the bottom here, the square base. Okay. And then my height is this x. And the volume of the box is 500 centimeters cubed. What are the dimensions? Okay, so here we go. We can represent the volume as the length of width times height. Okay, so if we know the volume is 500, that's going to be equal to the length, which is x plus 5, times the width, which is x plus 5, times the height, which is x. That bigger there. Okay. And so if I expand this, let's do that. So let's x plus 5 times x plus 5 is x squared plus 10x plus 25. And if I multiply everything by x, well, this will actually become x cubed plus 10x squared plus 25x. And that's equal to 500. But if I want to solve an equation, generally speaking, we put the 0 on one side. So if I subtract both sides by 500, I will have x cubed plus 10x squared plus 25x minus 500 on the right side. Okay, so again, we're going to have to apply a factor theorem. Try and find a factor here. Going ahead, what one of the factors are. Let's try 5, right? If I tried the volume of 5, let's see if that works out, right? So 5 cubed is 125 plus 10 times 5 squared is 250 plus 25 times 5, which is 125. That adds up to 500. And when you subtract 500, you get 0. Okay, so x minus 5 is a factor. Okay, but you might not necessarily tell that just from the first diagram, because the diagram could putting in the 500, right? If it was any other volume, it might not be a factor, and you still have to carry out the factor theorem to find a factor. So if we put this into our synthetic division, 5 being our kind of divisor, putting the coefficients, we have 1x cubed, 10x squared, 25x, and minus 500. Carrying out the steps of our synthetic division, we're going to see that we have a quadratic quotient. 15 times 5 is 75, 25 plus 75 is 100, and then we have 500, and then 0. So here we have the volume of our box equal to x minus 5 times x squared plus 15x plus 100. Okay, so once you're at this point, you have one solution from x minus 5, x, which is x equals 5. If you want the whole volume, whole equation set equal to 0. But is there a solution from this quadratic? Well, first of all, you can't further factor this. Okay, there are not two numbers that multiply to give you 100 and add up to 15 at the same time. So it doesn't factor nicely. But then you can ask, well, does it? Can I use a quadratic formula, right? And you could certainly try, but then you'll discover, okay, if I did b squared minus 4ac, let's see, 15 squared. You'll quickly discover, yes, so 15 squared minus 4 times 1 times 100 is a negative number. So that's not going to yield any roots. And so our only solution is x equals 5. This one here is extraneous. All right, so with x equals 5, we can proceed to answer the question, what are the dimensions of the box? Well, the length, the width, and the height are going to be 5 plus 5, which is 10. Width is 5 plus 5, it's just 10. It's a square-based box, and then the height is just 5. So 10 by 10 by 5, 10 centimeters by 10 centimeters by 5 centimeters are the dimensions of the box. Okay, so that is it for this lesson. Try some of the practice exercises from the textbook. Come to class with questions, and we will see you in the next video.